So I just wanted to make a quick announcement before we begin with the lectures again. So all the people who have come here from outside Bangalore and who are at UTC, who were here on the bus in the morning, you should please have your dinner somewhere around here. So I think our volunteers will be able to point out good restaurants and eating places to you. And you should assemble here sharp at 8:30 for your pickup back to UTC, because they have a cutoff. And so we want to transport you back there before the cutoff. And just in case you wanted to be adventurous and miss the bus, then you'll have to find your own. Yeah, the cutoff is 11 p.m. But we want to be well within their cutoff. And so we want to transport you back at 8:30 p.m. But if you wanted to stay longer, then you'll have to find your own way. So, but then please do make it back there. I would encourage you to actually assemble here at 8:30 and take the bus. Was that it for announcements? Yeah. So we'll begin the afternoon session, and we're very happy to have Professor Ashwin Nayak with us here. He's from the Institute for Quantum Computing, and which is at the University of Waterloo in Canada. And Ashwin is going to give us some, what is the first one? Theoretical quantum information.
Something about theory.
Yeah, some theory stuff. Yeah, no experiments, but it should be fun still. Okay, thanks.
Thanks, Urvashi. So, it's always a difficult task to introduce a new subject to an audience that I hardly know. I decided I would focus on the basics of the field as viewed from the point of view of a computer scientist or a mathematician. And perhaps this introduction will make talks by computer scientists or mathematicians working in the area of quantum computation less intimidating for you. So it's more basically an exposure to the language that we use, or at least the very basic elements of it. So I had a more ambitious plan, which would involve an introduction to a topic that is of a lot of interest today, which is semi-definite programming and its use in quantum computation. And my goal will be basically to lead up to that. That's in today's lecture. So the third lecture I give, which is tomorrow afternoon at the same time, will be on that topic. And today's lecture will set up for that. You won't see, much of the fireworks that quantum computation comes with in this lecture, but hopefully I'll make up for that tomorrow. Okay, so the goal will be to familiarize you with these notions. And some of these would be known to you in some form or the other, but I'd like to put it in a formal setting, on firm mathematical footing. So I'd like to talk about quantum states, quantum operations, measurements, and measures of distinguishability for quantum states, so metrics on quantum states. And these are all notions that you will encounter in almost every talk in this area. So far, you've seen quantum states as in terms of qubits. When we think of a physical system, mathematically, it corresponds to a Hilbert space. And in this talk, I will limit myself to finite dimensional Hilbert spaces. So we have this correspondence between a physical system with, let's say, d degrees of freedom, which mathematically will be described by a complex Euclidean space of dimension exactly d. And in this talk, I'll denote such spaces by calligraphic letters. like H, when I know the dimension, which is, in this case D, I might even write it as C to the D. Now, any particular state of this physical system, as you've seen so far, is a superposition of these D possibilities, right? So that particular kind of state is known as a pure state. A pure state is a unit vector, let's say V, in C to the D. Okay? And in physics notation, this is often written as ket V. And mathematically, we think of this as a column vector, just in case you wish to later on do some calculations. It is useful to think of it this way. Now, a physical system like this can arise from, different possibilities. One of which could be a particle which has, let's say, D energy levels. Or alternatively, you can think of this system being comprised of several smaller particles, each of which, let's say, is a two-level system. And in that case, this Euclidean space takes on a very special form mathematically, and of course also this is reflected in how it behaves physically. Let's say you have two such subsystems coming together. So if the system consists of two parts, each with two degrees of freedom, then the joint system has dimension 2 times 2, which is 4. And the underlying space is actually the tensor product of the two individual spaces. And this extends to multiple parts. So if you have an n part system, each consisting of two-level particles, then the underlying space is C squared tensored with itself n times. Something to note here is that the dimension of this space is 2 raised to n. So n particles, each of which has two levels, give rise to a 2 to the n dimensional space. And the fact that such a system can exist in a superposition of such a large number of states is one of the reasons behind the exponential power of quantum computation. So let's I'm going to be using this state over a system with two parts quite often. So let me just write it down here. You've already seen this terminology that we use for a two-level system. It's called a qubit and denotes a fundamental unit of information or memory in quantum computation. So for example, the state V, which is given by 0, 0 plus 0, 1 plus 1 0 minus 1 1 is one such state of 2 qubits. Now, this notation is used, this juxtaposition of 2 zeros next to each other denotes a tensor product of the 2 states. And the 0 denotes basically one of the 2 states and 1 the other. And you've seen this notation in Barry's talk. And I think also in Stevens, so I won't belabor the point. Now, this is not the only kind of state one encounters in quantum computation. In fact, something quite extraordinary happens when you try to measure what the state, or basically test what the state of the first of these 2 qubits is. When you try to observe this, what happens is you see each of the possibilities that occurs in this superposition with a certain probability. So when the first qubit is measured, and you're familiar with this, I'm just going to write it out directly. With probability 1/2, you observe outcome 0. And with the same probability, you observe outcome 1. And what happens is that the second qubit collapses to a state that is consistent with your observation. So in the first case, the state will collapse to a superposition of the first 2 possibilities, which, when you renormalize, comes to 1 over square root 2. And I'm going to write down only the state of the second qubit because you have the state of the first here. So it's 0 plus 1. And similarly, in the second case, you have this as the residual state. Now, the reason I wanted to go through this exercise is because, well, imagine what happens in a situation where the 2 particles are actually first prepared in this joint state, this entangled joint state, and then I take one particle with me and someone else takes it away with herself, right? And let's say my partner has the first qubit and makes this measurement. What happens to my state? How do I describe the state of my qubit, the second qubit, after the measurement has been performed? It's actually given by this very ensemble out here. With probability 1/2, I would have this state. With probability 1/2, I would have the second state. That kind of state, which is a distribution over superpositions, is called a mixed state. So such a state is a probability distribution over superpositions. And I'll denote it by a sequence Pi ket Vi. For simplicity, I'll work only with finite probability distributions, but in general, you need not restrict yourself to those. So this index set I will go from 1 to some m for some m. Right? So here Pi are bigger than or equal to 0 and sum up to sum up to 1. Now, when a mathematician talks about a quantum state, this is what they mean. They mean in this general state, a general mixed state. And when they wish to talk about pure states, they specify that it's a pure state or a superposition. Now, so this particular representation of a mixed quantum state is quite cumbersome to work with. Instead, we often work with what's known as the density matrix corresponding to the state. So the density matrix corresponding to this state here, the mixed state, Pi, Vi, is given by rho, which is a convex sum, I going from 1 to m, of Pi, the outer product of Vi with itself, where this bra Vi is basically the conjugate transpose, so the adjoint of this vector. So think of this as the row vector with the entries conjugated. So just so we get some familiarity with all these concepts, I'm going to work out simple examples, and they're generally going to be derived from this particular state here. So for example, the density matrix, let's call this example 1. The density matrix corresponding to qubit 2 in example 1 is given by this uniform combination, which is 1/2, and now I take the outer product of the first vector with itself and then 1/2 times the outer product of the second. So this looks like 0 plus 1 over square root 2 and its conjugate transpose here. This is a matrix product and a similar matrix product for 0 minus 1. Right? And if you do the algebra and you simplify it, what you'll see is that this equals 1/2 outer product of 0 with itself plus 1/2 the outer product of 1 with itself. Now, something curious to notice about this is that this is also the density matrix for a different mixed state. Do you see which one? Of 0 and 1. Sorry, the density matrix for the mixed state for this mixed state here. Right? And this mixed state is different from this one, at least at the face of it. But nonetheless, they have the same density matrix. And the reason for this is something we'll encounter later. It's that although you may have different probability distributions over pure states, which lead to different mixed states, those two mixed states may not be physically indistinguishable. So they would behave the same under unitary evolution, or if you want to make a measurement of it. So two different mixed states may have the same density matrix. Okay, having said this, I'd like to point out a few obvious properties of density matrices. The first one is that this matrix is a positive semi-definite matrix. Now, what does it mean to be positive semi-definite? Well, there are several different ways of understanding it. One is that it is a Hermitian matrix with non-negative eigenvalues. The second one is that for all vectors in this underlying space H, this inner product V rho V is bigger than or equal to 0. And there are several alternative but equivalent ways of writing this. I'll use this particular definition. The second property is that it has trace 1. So what is the trace? Again, there are several different ways of defining trace. If you look at it as a matrix, then the sum of the diagonal entries is the trace. And alternatively, you can write it as the sum here. The trace of rho is a sum over j going from 1 to d, e sub j rho e sub j, where e sub j is any orthonormal basis for the underlying space H. Okay. Now, fact is that these two are properties that entirely characterize density matrices, meaning any matrix or operator satisfying 1 and 2 may be written as the density matrix, or is the density matrix of some mixed state. Okay, and the reason for that is quite straightforward. let's say the matrix is P. We know that every positive semi-definite matrix, or at least one should know, that it is unitarily diagonalizable. So P being positive semi-definite, and I abbreviate that as PSD. Let me write that down here. Positive semi-definite implies that P may be diagonalized as a summation over J going from 1 to the dimension of the space lambda I. Let's write it as UI bra UI, where the lambda i's are all non-negative. They are the eigenvalues of P, and the UI's form an orthonormal set. Oh, sorry, this is J. Let me just use J. I was using I for a different index. So once you write it like this, you see immediately what the underlying mixed state would be. This is the density matrix for the obvious mixture, which is lambda I, sorry, let's stick to J, lambda J, Uj. Right? So it makes sense to identify density matrices with quantum states. Meaning, whenever I talk about a quantum state, I mean some density matrix, which may be pure in specific cases. Okay, let's see where we are. I think I've told you a lot about quantum states. I should move on to operations. Yeah?
Earlier we had the example where there were two different states at the same density.
Mm-hmm.
So how can you differentiate two states in the density matrix?
Okay, so we had this state here and another state, another mixed state that had the same density matrix. Turns out, whenever that is the case, there is no way to physically tell them apart. Meaning, you let them evolve under some Hamiltonian, let's say, and then you make some observation. No matter which Hamiltonian you pick, no matter how cleverly you design your measurement, the observation, the final, the outcomes that you will see will have the same probability distribution for the two mixed states. Meaning there will be no difference between the outcome of the first experiment versus the second experiment.
That means we can rearrange this expression also and write it.
Yes, there may be several different ways of writing this density matrix as a mixture of pure states. Yes. And later on, I'll give you a reason why. You'll see actually why these are physically indistinguishable. So I'll prove the statement that I just made.
You didn't talk about entangled state yet.
No, I didn't, and I may not, because I may not use them. I mean, you've seen this example of a state that I gave, the 2-qubit state is an entangled state.
All mixed states are not entangled.
Not all mixed states are entangled, no. I won't, I won't address that issue in any of my lectures, so it's a huge area by itself, and I just won't have time for it. That's right, yes.
Those two are the completely mixed states, the maximally mixed ones, both of them. No?
That's right, yes.
That is why they are indistinguishable.
Okay, so let's see. I'll give you another example of two states, of two mixed states that are not the completely mixed state but are still physically indistinguishable. So consider these two states. One is, well, I'm going to write it as, pictorially. So let's say this angle is theta. This is ket 0, this is ket 1. So this is basically cosine theta 0 plus sine theta 1. And this one is cosine theta 0 minus sine theta 1. So let's call this u0 and this u1. Okay? So let's look at the mixture 1/2 u0, 1/2 u1. And the second mixture we can consider is a simple mixture of 0 and 1. So this occurs with probability 1/2, as you can see here. And this, sorry?
In the previous case, the theta was 45.
That's right.
So it's the same.
I'm sorry?
So it's the same, right?
What is the same?
When the mixed state representation of u0 and u1 will be the same as the mixed state representation of 0 and 1.
It's not because of the angle. There's no, it's just that it's an equal combination of a symmetrically placed state, right? That you will get, as you said, a mixture of 1 and 0, but they will not be equal. It won't be maximally mixed.
Yeah.
Okay? So here, the mixture here I want to look at is cos squared theta 0 sine squared theta 1. So these two have the same density matrix. And that density matrix is given by this 2x2 matrix. Okay, so this is not in general completely mixed, so it's not 1/2 the identity, but nonetheless you will see that these two are indistinguishable from each other. Okay, so let's move on to operations. You're actually familiar with two kinds of operations in quantum mechanics. One is the evolution of a physical system in an isolated manner, in which case it evolves according to a unitary operation. And the second one is a measurement. So the first one, let's write it as unitary evolution. The second, I don't want to write this as a measurement just yet. Actually, although it's equivalent to one, let's write it as discarding a subsystem. So what I'd like to do is to tell you, tell you what these things look like mathematically, and correspondingly, what these look like when you talk about quantum states in terms of density matrices. So, in the superposition picture of quantum states, when a state V evolves according to unitary operation U, and when I want to denote an operator on space H, I'll use this notation L of H, meaning linear operators on H, and U being in this is by definition. The resulting state is, of course, again by definition, U applied to V. The reason I write this down is because I'd like to show its connection to mixed states. The mixed state Pi Vi evolves exactly as you expect it to be, meaning if you're in state V sub I, then the resulting state will be U applied to V sub I. And the resulting density matrix is the same combination of UVI. So it's I going from 1 to M, Pi, UVI, times its conjugate transpose, which you can write as that. And now you see that because a matrix multiplication distributes over addition, you can write this as U times summation I Pi VI U conjugate transpose, so U adjoint, which is precisely U rho U adjoint, where rho was the original density matrix. Right? So a density matrix rho evolves under U according to this rule. Okay, let's see what happens when we focus on one part of a two-part quantum system. So let's say rho is a density matrix on the space H tensor K. So mathematically what happens is, well, we can derive the state, the reduced density matrix of rho onto any one of the two spaces by taking what is called the partial trace. If I want to be consistent with that notation, I should, okay, let's do the second, just to be consistent with that notation. I'm choosing the basis 0, 1 for the second qubit. So this is what it's going to be. And let's write it down just once. So when I multiply I tensor 0 with rho, I'm going to get only those terms here that have 0 in the second qubit. So I'm left with 1/2 0 plus 1, and similarly I'll have 0 plus 1 from this side, and I do the second, I compute the second, I get a similar sum, where only those terms where I have 1 in the second qubit remain. Okay, and you see that this is also the completely mixed state once you simplify it, and you see that it's the same as what you got when you made, what you would get if you made a measurement of the second qubit. In the standard basis, I mean in the 0, 1 basis or in any other basis of your choice. So disregarding one subsystem of this bipartite system is effectively the same as measuring the one that you're discarding. Now, the reason I wanted to talk about partial trace is because the reduced density matrix captures the entire behavior of the big state, provided you are only focusing on the reduced, one part of the system. Okay? So if all your operations are on H and you never touch the K part of the system, you measure only the H part, then all the information that you're going to get from the big state rho, the joint state, can be derived entirely from the partial trace. So the partial trace captures all the properties of rho when the operations are restricted to H. Okay, so as I said, these are two familiar operations that you might have seen in quantum, in the context of quantum mechanics. Turns out that these are, you can do any other physically realizable operation by taking a combination of these two. So every physical operation may be obtained by a sequence of unitary operations and partial traces. In any order you wish. What's even more remarkable is that no matter how many of these unitaries you had and how many subsystems you discarded, how many you added, finally that net physical operation, the net quantum operation that you get, has a very simple form. And this form starts with simply appending an auxiliary quantum system, applying a unitary operation, and then discarding part of the subsystem.
Excuse me, I have a question. When you are talking about reduced density matrix, for subspace H and K, that's for the H and K is equal. Exactly that's true when temperature is 0. I'm talking about physical. When temperature is 0, reduced density matrix for subspace H and K is equal.
Well, not necessarily. So at temperature 0, you expect the state to be pure. You expect not a mixture but a pure state, in which case the two paths will have the same spectrum but may not be necessarily the same. They'll have the same eigenvalues mathematically, but one may be a mixture of
And when you have this small temperature there, how much these two matrix reduce density matrix can be different in each other?
Well, I imagine that would depend on the physical system you're talking about. I'm sorry? Yeah. So it depends on the physics of that particular system. I mean, I guess that's the best answer I can give.
So you said that the reduced density matrix on H and reduced density matrix on K are not necessarily equal?
In zero temperature is equal.
But I thought they should be, and that's how you get this area law for entanglement and...
So for a pure state, the spectrum of the two reduced density matrices will be the same, the spectrum. But if you look at, the first density matrix may look like, quarter probability on 0 and 3/4 probability on 1, whereas the second density matrix may look like quarter probability on the 0 plus 1 state and, 3/4 on 0 minus 1 state. The von Neumann entropy is the same, yes. Because the eigenvalues are the same. Okay. So here's a theorem. And this is attributed to Steinspring. Actually, I'll restate this theorem once I define a few more terms, but for now, let's write it as this. Every quantum operation that maps density matrices over H to density matrices over K may be written in the following form. So let's give this a name. Let's call it phi. The action of phi on a density matrix rho over space H can be written as the partial trace over some state, some space, let's call it G of unitary U applied to rho. Okay, I'm going to write it as this, but some of my colleagues don't like this particular representation. Okay, let's write it like this. Where U is a unitary operation well, maybe I should, I'd like, let me just make a small change here. Let's write it as U rho U dagger, where U is a unitary embedding, or what's known as an isometry, from H to K tensor G. Okay, an isometry or a unitary embedding is basically a map which it's a linear transformation which preserves norms. So an isometry is the same thing as saying that U adjoint U is the identity. Okay? So U maps rho to a larger space which is K tensor G, or equivalently, as I'd written earlier, you append some ancilla qubits, so an external, an auxiliary system, apply a unitary transformation, so that's how we think of doing this embedding, and then you trace out the part of that bigger system that is no longer of interest to you. Okay? So no matter how complicated the sequence of operations was, you can simplify it to this two-step operation. All right. I should point out a couple of properties of quantum operations, in particular of unitary operations and partial traces. And these are basically its defining properties. Just like the defining properties we had for states. One, which is the obvious one, which is that they map quantum states to quantum states, meaning positive semi-definite matrices to positive semi-definite matrices. And two, they preserve trace. So that's how they preserve density matrices. So let's write these down. Let phi be this quantum operation. Phi of rho belongs to, well, is, or let me write this as phi of x is bigger than or equal to 0. So I use this notation. So this, this is a dense, well, this is some matrix phi is some some operation like this, right? Operating on a matrix, it gives you another matrix. That matrix is positive semi-definite. So this is some notation I'll introduce in more detail tomorrow. All it means is that all the eigenvalues of this matrix are non-negative. In particular, so this is a Hermitian matrix and its eigenvalues are non-negative. The second thing is that it's trace preserving. So the trace of phi of x equals 1 if, actually, let me just write it as, it's easiest to write it as trace of x. And this is for all positive semi-definite operators. Okay. Fact is that phi satisfies a much stronger condition than the one I have written out here. Not only does it map positive semi-definite operators to positive semi-definite operators, it does that even when you apply it to a part of a bigger system, which is normally how we view quantum operations. Even when you do an experiment in your lab and you think you're applying some Hamiltonian to your, something you confine to your lab, what's happening is that you're doing nothing on the rest of the universe. So that's similar to basically acting on one part of a much larger subsystem. So 1 star is the stronger property of quantum operations. Imagine doing nothing on the second part of a larger quantum system. So take a density matrix Y on any space H tensor K. Apply phi to only one part of it, the part that corresponds to H, and still you end up with a positive semi-definite operator. This property is called complete positivity. So all quantum operations are completely positive and trace preserving. And in fact, this theorem due to Stein-Spring applies to all completely positive trace preserving operators. Okay.
Is there any non-trace preserving quantum operations?
Yes, sort of. So, so often we think of doing post-selection, meaning, you prepare a system in a certain state, and then you make a certain measurement, and you wait for a particular outcome, right? Let's say, in our example, we wait for outcome 0 when we are measuring 2 qubits, and we are measuring one of two qubits in the basis 0, 1. Then that operation which takes you from the state of the two qubits to one qubit when the outcome is 0 is not trace preserving in general, right? So there is occasion to think about non-trace preserving quantum operations. Right. So the partial trace operation. So the partial trace operation is also trace preserving. Yeah, the part that remains. Yes. Okay. Let's see. I have maybe 10 minutes. Is that right? Okay, so in that time, I will, I think, finish talking about quantum measurements. And I may not get to metrics, or maybe I will. Let's see. I'll try. Nothing, so all physically implementable operations are completely positive.
But can some operations which don't give complete positive, can they be used as some signature?
Okay, so mathematically we can think of operations that are not completely positive. For example, if you take there is this operation called the partial transpose, and so let's see how this goes. So the action of this so it acts on a bipartite state. It acts on density matrices on a tensor product of spaces. Takes it to the same space, and it's defined as the linear extension. Let me call this, script T. So it takes a density matrix, which is of this tensor product form, to A transpose tensor product with B. And because you have a basis for the entire tensor product space of elements consisting of tensor products, I mean this defines the operation on the entire space. Now this operation is positive, but not completely positive. And as far as I know, there is no physical way of implementing this operation. Meaning there's no experiment in the lab that you can conduct that will implement this. Okay. So let's see what quantum measurements are. In our example, the very first one, where we had this joint state of two qubits, we observed the state of the first qubit, or the second, I forget which one, in a particular basis. That is an example of a very simple kind of measurement, a projective measurement. Or a von Neumann measurement. Mathematically, this is given by a sequence of projection operators, orthogonal projection operators. This is specified by a sequence pk of orthogonal projection operators let me use this abbreviation on the underlying space H. This basically means, what does it mean to be orthogonal? It means, one, that if you take any two of them, so pi times pj is 0 whenever I is different from j, and 2, this is a projection operator, so each of them is a projection operator, meaning it squares to itself. And the third property it satisfies is that the sum of these projection operators, the sum over k of pk, is the identity on H. Such a sequence is what defines a complete measurement. Sorry, not a complete measurement, but a von Neumann measurement. Now, you might ask what happens when you make this measurement. So when a state rho is measured according to this measurement, you get outcome I. So the indices here, k or I, they denote the outcome of the experiment. So they might denote the spin that you're measuring, or they might denote some other property of the system. You get outcome I with probability which is given by the trace of pi times rho. Rho is this density matrix that we are measuring. And the residual state, let's call this little piece of I. And the residual state is basically pi rho conjugated with pi divided by the probability that you observe outcome I. Now, this is not the only kind of measurement you might make. You might think of doing a more complicated experiment. You might let the system evolve according to some Hamiltonian, and then you may wish to measure the spin or some other property of interest. When you do that, the description of the measurement mathematically becomes quite different from what I've written here, but it's not all that much different. More generally, such a quantum measurement is specified by what are known as POVM elements. I'll just use a different letter here, E, to distinguish it from an orthogonal projection measurement. So a sequence EI where the EIs are positive semi-definite, meaning, well, in my notation earlier, I write it as EI are bigger than or equal to 0. So that's the first condition. And the second condition is that they sum up to the identity. So I, summation I, EI, is the identity on H, if the state that you're measuring is on space H. Okay, so in the literature, this is called a positive operator valued measurement. I have no idea where this nomenclature comes from, and I think its use is on the decline. I tend not to use it. But you're likely to see it in the, in the books and the papers that you read, so it's good to know what it is. POVM. Now, the action of a POVM is quite similar to that of an orthogonal projection out here. The only difference is that there is no way to tell what the residual state is unless you know how this measurement has been implemented. What the underlying unitary operation is and what the corresponding von Neumann measurement that followed the unitary was. So when state rho is measured according to I'm sorry? So I think you're thinking of the sort of the cross operators corresponding to this measurement, in which case, I would have written it differently, in which case EI dagger would be positive semi-definite, and then its sum would be identity. But here I'm thinking not of the cross operators, but the POVM elements themselves. So when the state is measured according to EI, outcome I is observed with probability trace EI rho. But the residual state depends on the unitary and orthogonal measurement used to implement this measurement. So implicit in the statement that I've written here is that every general measurement, every POVM, can be implemented as a unitary followed by an orthogonal projection operator. Because I don't restrict the EI to be projection operators anymore.
But then ultimately it's a unitary followed by a projection.
That's right.
So
Yes. So can I elaborate? Okay. So what I missed in that that description is that yes. Let's do an example. It's a good. I have an example here, so it's very well set up. Let's take, I got this example from Barry's lecture. So here's an example. This is his Schrodinger cat circuit. So let's imagine doing a measurement on rho by first applying a Hadamard gate on it. So this is a 1 qubit unitary, which I'll write down in a second. And well, then you take an ancilla qubit, initialize it to 0. Let's see. You know what? I mean, in this particular case, it will turn out to be a projective measurement, but that need not always be the case. Good point. It was only to illustrate,
Can you give an example of an actual experiment where we don't do a projective measurement? What does it mean to do a non-projective measurement? Not just project onto something, right?
Right.
When you measure, then it's, I mean, I don't want to use the word, but you can say it's collapsed onto a particular state.
Right.
So then what?
So what's non-projective about it?
Yeah.
Okay, so let me just say this. Okay, so maybe I'll make a different diagram here. Let's erase this so it's not confusing. So you have a state rho. It lies in some space H. So you do an experiment by, so what you do is you combine it with some subsystem that's initialized to some state, 0, right? Then you apply some unitary to it, U, right? And then you do a measurement, you do a projective measurement of that sort. So you get outcome I with, well, the state collapses to this when you get outcome I, and the probability with which you get this is the trace of this state, right? Okay, so we have mapped rho to this state, right? So rho has gone from here to here, right? And this is a state in a larger space or a smaller space, depending on whether you discard part of the system or not. Okay, so how do I describe this operator in its entirety that acts on H, takes me to some other space, let's call it K. That operator need not be given by a projection operator. So mathematically, this is a mapping, rho going to this state, right? Consisting of several steps. If I wanted to write it in one shot, how do I write it mathematically? Okay, so yes, that is right. But there is a simpler representation. So there is a way of writing it simply in terms of an operator EI, which you get by combining, PI, U, and that 0. Okay? And when you do that, then this EI will no longer be a projection operator. It will be a positive semi-definite operator.
So which is a subclass of which? I mean,
Mathematically, this is a subclass of
because
POVMs.
that is a more general thing.
Right.
So then what is a generalized measurement?
Projective measurement on the combined system will lead, if I trace out one of the subsystems, then that will have the form of this EI.
Right.
So in that sense, EIs will also include that.
That's right.
I
Yes.
can done a measurement of this system, that would have been that.
That's right.
Because there's both combined system, I'm doing a projective measurement on the whole system, and I trace out one of them, and that will have this form.
That's right. And I think but the source of confusion is, and this is something that I guess everyone should understand, that this is not so general that you cannot think of it in terms of the projective measurements. You can. And if you wanted to, I mean, you might make life more difficult for yourself, but you can only think of, quantum operations or measurements as unitary followed by a projective measurement. You can live your life like that, but it's a bit difficult. I mean, it's easier mathematically to learn this formalism as well.
Does the incursion of unitary lead to this measurement?
I'm sorry?
Does the incursion of, if you include unitary operations, does it mean that we are doing POVM and not projective?
Yes. Actually, let's see. Let me give you a different example, not Barry's example, because So let's just do this example here. I think it'll be. Right. That's essentially the case. Yeah.
It's not that one is higher set.
It's not giving you a more powerful set of quantum operations. It's yeah. Yes. That's. Weak measurements. Actually, weak measurements are, I'll just say one sentence, the one sentence I know about it, that, there are special kinds of measurements, right, where the residual state is close to the original state. Non-perturbative or, slightly perturbative measurement, right.
But it's not, it's a different sort of measurement from a projective measurement. Because
It could be a projective measurement.
could be, but
Yeah.
may not be.
It need not be, no.
That might be an example of a non-projective
Yes, I mean, there are examples of weak measurements which are not projective, yeah.
There would be a partial trace over it, like the rho is going to.
I'm sorry?
There is a partial trace over it.
Yes, I mean, this was, so far it's only a projective measurement. If I included a partial trace, then I would get possibly a non-projective measurement.
So I'm saying that the effect of the EIs,
Mm-hmm.
the effect of the EIs, that's there because there is a partial tracing, right? From rho is not going to that square. That is including a 0, 0.
Sure. Yes, maybe the confusion is because I write PI like this, but let's see. Maybe it's time to wrap up.
Yeah, because Barry has to
Yes.
leave for the airport right
Right.
after his.
Right.
Sorry about
So
this.
maybe I should just, I think we all understand POVMs very well. It's just that I didn't write it clearly on the board, and I'm happy to elaborate separately.
Sure. If there's no pressing question, maybe we'll stop. Yeah, we'll stop this before. Yeah. So, thanks a lot.
Oh, thank you. Thanks.